Once again, I want to thank the organizer and impressive and hardworking and well organized, and so especially Professor Jiazu Zhou. So today actually is one continuous talk. Like yesterday. Since yesterday I already introduced some preliminaries. So today we're going to some little detailed. Okay. First, like yesterday I introduced some okay, maybe this way because they're too close there. Okay. And so I will see. First of all, what's the kinematic formula? Because yesterday I used the formula to get some inequality.
This one because it's so
okay. Just okay. Yeah. Okay, I just speak louder.
Yeah.
Okay. So, if we have a group, the G be a Lie group. What's a Lie group? That's a manifold equipped with a group structure. Okay. And G a compact subgroup of G, so H. Then we have a homogeneous space, G over H. We assume this has an invariant Riemannian metric. And also this equivalent is say an invariant density dG. Okay, MP, NQ be two compact submanifolds. And this is P means the dimension P, and Q is the dimension of N. We assume that P plus Q, that's the dimension of M, dimension of N, minus the dimension of ambient space. This must be positive. What this means? This means that you always have the intersection. And otherwise, the intersection is some set of measure zero. That's what we want to avoid that. So let this I and P intersect with the G and N. What's the G N? This is a G. That's a group. That's we call this motion, a rigid motion. Okay. This is an integral invariant. What's called the integral invariant? Then I will introduce a little later. Of the intersection. So this is the intersection, and this is the invariant of this intersection. Then many works in integral geometry have been concerned with evaluating the integral of this type. Okay. This invariant is dependent on G. When we have G, you have intersection. Then you have this one. This invariant, and then we want to take the average. Okay. Then we want this integral in terms expressed in terms of invariant of this M and N. Let's know. So this is called, whenever you have the integral for this, then you get a kinematic formula. Okay. Okay. So let's look at that. This is N. Okay. This is M. They are far away, for example. Then you take the G. Okay. Take the G as the motion. Register motion or just isometry of the G, depends on the G. Because according to Klein, Erlangen program, and every geometry is invariant under a certain group. Okay. So therefore, this intersection here. You have the Gn, move the n to here, then you have the intersection. So therefore, we want to take the invariant of the intersection. Invariant could be the volume, the surface area, or the curvature. Okay, the curvature, mean curvature, and the principal curvature. Okay, and the curvature. So that's the invariant. Okay. Okay, then we see. Okay, so then we have the formulas of Poincaré, Blaschke, and Santaló and Howard. Okay. And if G is a group of rigid motion in the Euclidean space, okay, ambient space is Rn. If this invariant is just the volume of the intersection, volume, then we get the integral of this just equal depend on the volume m and n, and over some constant. Okay. The constants depend on n and pq. Okay. So especially let gamma 1, gamma 2 be two rectifiable curves in R2 of length L1, L2 respectively. Now we take what's this intersection. We take the number of intersection because the two curves, the intersection, the invariant, maybe some, that's the intersection. The number of the intersection. Then this Poincaré is 1912. They get this beautiful formula. Okay? What this means? Okay, this one you have, for example, you have a gamma. This is gamma 2. Okay, if you have gamma 1. Okay, then you have the G. Okay, then you get this gamma 1. Okay, this is G gamma 1. Okay, then you count this intersection. This is a point. Okay, 1, 2, 3, because this is 3. Depending on the G, because this is G, you can move, then this is the change. Then you get this formula here. What's the formula for this one? Okay, for some set, okay, for some set, you can count the volume, but for the discrete sets, the volume is the number of the points. Okay, so so this one is exactly the volume. Okay, so for the curve, what's the curve? The volume of curve is the length. Okay, we say the volume. That's the general meaning. It's not really the volume. Okay, the volume, if this one-dimensional, the volume is length. Okay, two-dimensional, the volume is the surface area. And three-dimensional and high-dimensional, you can have some volume. Okay, so this is one. And if let G be group of rigid motions in Euclidean space Rn, if this be one integral invariant arising from a wild tuple formula. Okay, this is then evaluation of integral 1 gives a kinematic formula of a Federal and Chen, SS Chen. Yeah. And if G be unitary group acting on complex projective space, and Mn are complete analytic submanifold of Cpn, still let this be volume. Okay, so the integral 1 leads to the result of Santaló. If this be the integral of Chen class, in the integral leads to a series of Schifrin. Okay. Okay, so, and this one. Okay, what we just introduced this time? Because for the manifold, if you move the manifold, they have the intersection. This intersection. For the intersection, they have basic sense, volume, and also curvature. Okay, the volume is called intrinsic. It depends on the submanifold itself. Okay, the curvature is dependent on the immersion and embedding. Okay, that's the dependent on embedding. So we call that curvature is like the extrinsic invariant. And also there is another one, invariant. We call the topologic. For example, okay, Poincaré characteristic. Okay, we call that formula. Okay, so this one. This SS Chen, the kinematic formula. They choose this I be the intersection of the topologic invariant. That's called the so therefore, okay, let M1, M2 be two domains in the Euclidean space Rn. That's domain. Domains with non-empty interior. Okay, that's domain. So with a smooth boundary, and assume that for any G, okay, and is a group, the member of group, the group of registered motion, we take the registered motion. The component is finite, okay, just like this one, okay, like this submanifold, you move that. We want the intersection is finite, okay, the finite, okay. So therefore, and the group, then we have let us H, this H, because the each for each. Okay, if you have each for this one, if this is a, okay, this is a M1, okay, this is M2, this is if this is M1, okay, this is M1. Yeah. For each, they have, okay, they have this is okay. This is partial, this is partial can 1. Then they have the couple, okay, 1. Couple 1, this is a 1, okay. They have couple minus 1, that is a 1, okay. So therefore they have, this is a principal curvature, okay. Principal curvature. So the principal curvatures, and this is H's mean curvature integral. So this, what does this mean? This is H's elementary symmetric function of the principal curvature. Okay. So therefore, okay, we have, this is you can see that if you have the mean curvature here, this is kappa 1. For example, in general, you have kappa n minus 1. Okay. What's the H? And what's this is called the Hj, okay, this is called this Hj, okay, Hj, and actually it's something like this one. We get this 1 plus t ki, okay, then this I equal 1 to n minus 1, okay. Then we get this one, and we write the n minus 1. This j equal 1 to n minus 1. That is hj. This is tj. Okay, we do this way. We get this hj, this equal, and this n minus 1 is j, and okay, that is symmetric, elementary symmetric is a function of ki1, j1, and j1, and this is kappa j n minus 1. Okay, so this is defined by this way. Okay, so therefore this is defined by this way. So this is a 2 to the, also this is a integral. Okay, over boundary. So therefore, SS Chen, get this formula, beautiful formula. Okay, so this formula have many fundamental application in geometry and physics, and also recently they found the application in information science, and such the many of them. Okay, so this is V. This V is the volume of this K, M. So this is Euler characteristic. Okay. So this formula, when this is in N, when N less than 3, less or equal 3, this formula is belong to Blaschke. Okay. So S.S. Chen proved this one for general N. Okay. Okay. So this is another extrinsic kinematic formulas. Okay. So this is the one here. So this is the first proved by Chen in 1972 and by myself in 1992. So let K be two compact surfaces in Euclidean space R3, and with a C-smooth boundary. Okay, let this H K total be the mean curvature square integral. So let kappa be the curvature of a curve. Then we get this formula here. Okay, this is the one. F is the surface area. For this one, you can see that it's a, and you can imagine in R3, if you have a 2, okay, 2, okay, 2. This is M1, okay. This is M1. This is M2. Okay. Then if you have, okay, this is M2, this is M1. Then you have the G, okay. Then, okay, you have this G. This is G, M2. So this intersection, the intersection G1 and G2 is the curve, okay? Is a curve. So this is a curve in R3. So this curve, they have a curvature. So you just use this curvature here. Use the curvature, that's the intersection. The curvature square. Then you get this formula. Okay. And later on, okay, that's and be generalized to higher dimension. If we have MK be two compact, smooth hypersurfaces in Euclidean space, and later this and be the mean curvature integral. This also the H elementary function of the principal curvature for K1 and the K minus 1. Let the H be mean curvature of the intersection, the mean curvature of this intersection. Then for M, so therefore we get this formula here. Okay. So this is for general dimension. This is one dimension in 3. This is dimension for any dimension. Okay. This is here. This is M equal 1. So everything is back to this one. Okay. Okay. So this is something. Okay. We that then we in integral geometry or in the geometry, because everything is depends on the measure. Okay. On the measure. Usually we say, okay, we say the length, the arc length, the surface area, or the volume. That means you want to see what is the measure. Okay, give your body, give your a sphere, for example, a sphere. If you say, okay, what's the measure for the sphere? You can see, okay, you can say means volume. Volume is a measure. Or you can say the surface area. I just say, okay, surface area. Surface area is also the measure. And you can have another measure. You can have many measure. Okay, depends on what you mean. So therefore, we must have some geometrical measure. Okay. I will say what's the geometrical measure. Then we can say all the measure we have seen are geometrical measures. Okay. So actually the curvature and volume are two basic concepts in global differential geometry. So if you're a geometer, they ask you, okay, what's the basic? What are you doing? Okay, and we said, okay, geometry is a study, and is a study of the geometric object. Okay, you can broadly say that. And also, what's the two basic? And one is the curvature. Okay, like we have 3 professors in this morning. They give some lectures. They always investigate something about related to mean curvature, principal curvature. That's a curvature. Okay, the curvature is basic one, and also another just volume. Okay, someone may wonder, okay, so how can you don't know the volume? Of course, we don't know volume. For some geometric object, we don't know the volume. Okay, we only know some volume, only for some specific geometric object we know the volume. Okay, so some recent researches are focused on integrals related to the variation of curvature and volume. These integral formula are based on the geometric measure on the set of a geometric subject. What's a geometric subject? Such as lines and planes. Also linear spaces in the Euclidean space are n. So this is a Grassmannian. Okay, this is just Grassmannian. And then convex sets and also many. Geometric inequalities is a study of geometric measure and called Haar measure in the measure theory, which are integrals over the group of isometry in integral geometry. Okay. So some many geometers they do some research. It's based on the measure. The basic based on the curvature. Okay, they can use the curvature to some classification, and to do a lot of work. Okay, so integral geometry deal with a problem in mathematics which have a strong background. The beautiful integral formulas established in integral geometry are fundamental in stochastic geometry, geometric tomography, and stereology. These subjects have found important applications in many other fields, such as imaging science, material science, biological science, medical science, information science. Okay. And a basic idea in integral geometry and the geometric probability is to define a measure for the sets of random elements which are geometric objects, point lines, congruent set, or strips, and so on. The measure choose is invariant under some group of transformation. This is based on Klein-Erlangen program. For example, the group of motions, the group of Fi transformation, or the group of general Lie transformation. Okay. So what's the geometric measure for sets in the Euclidean space? Okay. Geometric measure. Okay, let F be a family of a subset. First, you have a set, S. And then you have a family of subsets. These sets, we just put the sets, this in general way, which is closed under the unions and the intersection, and contains the empty sets. An invariant measure is a real valued function, not necessarily positive. Okay? Usually people will say, okay, we think about the measure is maybe positive, not necessarily positive. But satisfy for the empty set, its measure is 0. Okay. For the union of two sets, so therefore must equal the set of A plus the set of B minus the intersection. That is an intuitive way, right? Okay. So therefore, this is sure. For if someone in analysis you just look at the measure, then this 1 and 2 is just enough. Okay. Why we call that? We put the 3. The 3 means for the group of registered motion. Then this, if you have this, means the measure does not depend on the position of the set. Okay. If this set, the measure you here, then you have registered motion, you move to another place, the measure should be the same. Okay, this means. Okay, it's not depend on the position of this set. Okay, so you must have this 3. So therefore you have measure. So, okay, this is just a repeat what I just said. The measure is characterized by the first 2 simple axioms. The third axiom means that the measure mu A of subset A is invariant under the registered motion. That is, mu A is independent of the position for A in the space. Okay, that's the general. Okay, then this is the one. This is the one we just we had yesterday, and what we call the isoperimetric inequality, and this means, and for a domain in the Euclidean space Rn of the fixed surface area, the ball has the maximum volume. Okay. And then, okay, this is one. This is the one we really based on. Okay. Everything, okay, is based on this. Okay. So if we have 2 domain in the space, connected and simply connected, and bounded by a smooth hypersurfaces, okay. Let G be the group of isometry. That's registered motions in Rn. The dg be the kinematic measure. That's the measure. That's the invariant measure, the geometric measure. Okay. Then we have the following containment measure. So this is a containment measure. Okay. So what does this mean? This once again. Okay. I mean. So we have a domain. We have a domain. Okay. This is a dj. Okay. This is dj. Okay. Then we have okay. This is di. Okay. Then we have a motion. Okay. For example, this is g. Okay. This is g. Okay. Like this one. Okay. Okay. This is a registered motion. This is g di dj. Okay. We want to estimate those g such that this g contained in di or contains di, because we don't know which one is big or not. So therefore, we want to get the measure for those one. Okay. For example, this exactly contained. Okay, like this one. Okay. This is a g dj. Okay, this is what we want. We want this one, those g. How many of those g's? This g be many, maybe many. Maybe this is dj is big. Who knows? Okay. First, we don't know. Okay. Also, di dj, the position you can change is symmetric. Okay. So, what's this measure? This measure is they must intersect. Okay. They also they want this contained in there. This contained there. So the boundary cannot be intersect. So this is not. We must to those and then minus those the boundary contact. So completely inside. So therefore, this can be expressed by this one and minus this one. Okay. So what's this one? This is what this is. We just defined the geometric measure. Okay, satisfy not depends on the position. Okay, so therefore, this is just integral over this. So this one is what? This is I. We just take the one, take the constant, the I. So this is intersection. This is intersection. So this is dg. So therefore, my equal. This one is this one. This is a dg. So this is a intersection. This is also the boundary intersection. Is not empty. Okay. So therefore, we get this two integral. Okay. So this exactly equals this. So therefore, so if we can estimate the measure from below, okay, sometimes it is difficult, also impossible to get exactly the equal. So if we estimate this is below and this is above, okay, we estimate this above, estimate this is below, so therefore with this must be greater than, okay, then we can get greater than, we get the function of this. What's those A? Those A could be some invariant of the di and the dj. What's the di dj? Di dj, this could be some volume, surface area, maybe the mean curvature integral, the curvature integral. Okay, so this is called the invariant. So this is integral geometry invariant of D. Okay, so therefore we have this greater than this one. So therefore we immediately get it. So if this is a positive, this is greater than 0, then we know that this can be contained in there. So this be contained in there, or this contain this one. So if we let this di equal dj, so exactly the equivalent, then there is no g. So because d cannot be contained itself, right? So therefore, this is 0. So this is 0. So therefore, this we get this less than 0. So this is 1. What we want to get? This is 1 geometric inequality. Okay. Therefore, if we let the di be respect to the inbore and outbore, what's the inbore outbore? If we take this dj b, okay, what's the bore? Is correct bore, okay? For this bore, okay? If this is bore, Ri, okay? Or the circum, okay? Okay, this bore, okay? So therefore, this one cannot contain this one. This one also cannot contain one. They cannot contain each other, okay? So therefore, we get this less than 0, this less than 0. So therefore, in other way, if we let the di be the bore of radius r between this small bore and that bore, so therefore we still have this less than 0. So therefore, all kind of geometry inequalities could be derived by this method. Okay. So this is a general way we can get. So therefore, we look at and review what we have yesterday. We have L squared minus 4 pi is positive. So this is disk of radius L over 2 pi. Okay. So this is okay. This is L. This is D. So this is same as this L, and also the radius. Okay. This is L over 2 pi. Okay. This one. So therefore, for this all this domain, only this disk get to the maximum the area. Okay. So therefore, this is the one we have. That yesterday we have This we call this is isoperimetric deficit, and this is 1. Okay, if this is the domain, this is inscribed disk, this is circumscribed disk, then we have this formula here, inequality here. Then also Bodenstein inequality here. Okay, then this is what we have yesterday. Okay, in the committee. And so we want to get the upper limit. This is 1. So therefore we have this one here. So therefore actually we have this. We have this one here. So this is L squared minus 4 pi A. Okay. This is less than pi squared. This is rho m minus rho m. This is greater than, this is pi squared. This is R E minus R I. Okay. But for this side cannot be this case. Cannot be this case. This must be completely convex. Completely convex. Okay. Okay. Convex. So therefore, for this one you can see that. You can say this is this is RI. RI. This is this one is RE. Okay. But what's this one? For this one, this is here. This one is rho m. Okay. So this is much smaller than this one. Okay. What's this one? This one is very, for this one here. This one is side. Okay. Okay. This is okay. This is rho m. Okay. So this is multiple another disk very big. So this side is much large, much big. This one is not small. Okay. So this is between these two. Okay. Look like the very symmetric. Okay. Okay. So this is the one we have. Okay. This we just skip. And then we have the Minkowski sum and scalar product. That's what I introduced yesterday. And the two convex sets. Then we have the sum, and also have the scalar product, the homosity. That's our translation and a dilation. Okay. Okay. So this is a support function. Okay. So now. And yesterday, we just said we want to find the translation here, inside. So today we have a little condition, little strong. We move the translation, can move inside. Today I want the translation and a rotation. Okay? And the rotation. So let us Ki be convex domain of parameter. This L and A, and the Ki be convex. So this is convex. We consider the homosity copy of T. So this move in there. Okay, let's see. So this is Ki move inside, and also the rotation. So get the much big, much inside. Okay, so this one, the outside, and also the translation and the rotation. Yesterday only the translation. So let us Tm. Let us this G. This G is in there, the maximum. So this is the one. This is Tm. So the T capital M just in there. This move there and expand and such that this there. Okay, so this is more. Then because yesterday we just compare too. Okay, we just compare. Okay, this is a D with Okay, with this one, this L 2 pi. This is a disk. This is a disk. Okay. This is a D. We compare this D. So today we just compare the two. The one is this, one is this, one is this, and also we compare expansion and the rotation. Okay, then we'll get a two domain. This two domain, because the boundary, we can use the kinematic formula, just introduce it, and that's kinematic formula. So this is Poincaré's formula, get this number of this intersection. This get the 4T because for dilation. Okay. So if you have this is if this is a K, okay, if you have L and A is the area, okay, then you have dilation, okay, dilation. If this is okay, this is TK, okay. Therefore, the length for TK equal TL, okay, LK, okay. So AK is the area of K. The L is the length of K. You have this one, and also the L TK. The area TK is T square A. Okay. So you have this. Okay. So therefore, we get this Poincaré's formula for this one. Okay. And therefore, we have let M be the kinematic measure of the set, the position of G, for which have exactly n common point with partial K here. And if you have Ki here, okay, this is a Ki, and this is a Kj. And this is Ki, for example, you have, okay, this is Tki, the G, okay? So this is a number. This is 1, 2, 3, 4, the boundary. Okay. So this is a number. This is a number. This is 2n. For this one, if n is R number, that's measure 0 set. Okay. So this must be even. So therefore, for this side, you can write like this. For other side is a formula. And also, Euler Poincaré's characteristic of intersection. Then from the Blaschke's formula, we have this one here. So therefore, this is put to this. So it follows that. So for this one and this one, you immediately get the formula with this one. Okay. So therefore, we'll put a definition here. Okay. This is the one we call, for this one, we compare this one with the disk. Therefore, we have the delta 2. So this is a K and a disk. So the disk we write this is a B. Okay. B. This is a B. This is a B. Okay. The B. So this is equal L squared minus 4 pi A. Okay. If we have two domain, this one is not necessarily be the disk. So if this is a K, this is a K, I, and this, okay, could be Kj, okay? Therefore, we just compare this one. Okay, divide this one to this is ki, this is kj. This equal to the length square. This is the length square. His length square. Okay, minus 16 pi ai aj. Ai is the area of this one. Okay, this one. When you can see this one, since the convex hull of a domain increases the area, decrease. So therefore, for this, actually we can just consider the convex case. Okay. So therefore, with this definition, we call this mixed symmetric isoperimeter deficit Ki and Kj. Okay. Therefore, by these two formulas, we mitigate this one. This is what we just call the measure for the containment measure. Then we have the formula of Hartwig. Hartwig is this formula is 1934, and then by Ren and by myself, and this formula, this new formula here, this new theorem. And then we have this one more contained. So when this domain containing another, okay, so therefore this is a sufficient condition. Then immediately we can look at what's this. We can have, okay, we have this. We take this like the quadratic polynomial of degree 2. So therefore we have this one. What's this? This is not equal to 0. This is just this is a polynomial. This is just a quadratic one. Now we say that delta t equals this. Okay. So this is a t. Okay. This is a t. The figure for this one. Okay. So therefore Tm we have the capital M. Then we have the theorem. Okay. This theorem is 2 pi ai t minus this one less than 0 when t is between the m. This is like here, okay? Because we have two roots for this one, for this equation, we have two roots. One root is here. This is one root here. This is another root here. What's this delta 2? Delta 2 is symmetric, mixed, isoperimeter deficit. That's what we define, okay? Therefore, we immediately get this formula. This is inequality. Okay. Therefore, okay. What do we say here? If we take this one as a disk, this one as a disk, so therefore, this exactly is the isoperimetric deficit. So therefore, you can say this is L square I Lj square minus 16 pi square A I Aj. Okay. If one of this becomes the disk, so therefore this exactly is this one. Okay. So therefore we have this Boltzmann formula. Then we have especially we have this formula here. Then another inequality. Okay. Therefore, moreover, we get some Boltzmann-Stein inequality here. So this one is Tm. When Ki is a unit disk, so this formula led to the known Boltzmann kinematic isoperimetric inequality. So this is back to what we know before, this one. Okay? When one of this becomes a unique disk. Okay, so therefore we have a couple, many of this geometrical inequality, and also especially this one, and all this. Okay. Okay, that's all this one. If we take the one, Ki be the unique disk, then all this formula, okay, when let Ki be the unit disk, so the following Bohn's-Stein inequality are consequences of this symmetric isoperimetric inequalities. Okay, are those one. Okay, so those are generations of those formula. Those formula is like what I introduced yesterday. It's back to maybe range from 1920 until 2000. Okay, over 80 years. Okay, so therefore, I think I have to humanly just briefly renew. It's natural to ask if there is an invariant geometric significance such that we have this bound, because we already have this one, like here. Okay, it's low bound. Okay, so therefore we have the up bound. Okay, so that we don't know. Okay, and this until recent work. So therefore, by some inequalities, and which is one of my student Ma, and we have some formula. Okay, this is equivalent. This is a generation for this one. Okay, for the other one, just if this one is a unique disk, we get that one. This is for general case. So therefore, we have the up bound. We have the up bound. We have this up bound. So therefore, when one is when Ki is a unique disk, therefore we get this one, this up bound. Okay. So this one is also the work of Bokovsky, Hale, and myself and one of my students. Okay. Okay, then we have more, and what's this for? Convex polygon. Okay, because I want to prove, point out, because this one cannot be derived by Bothema, because Bothema we need that cannot be polygon, cannot be the boundary, cannot contain any segment. Okay, line segment. Okay, so therefore I have this. So therefore that's my talk. Thank you very much. Okay.
Are there any questions or comments?